Well, hello, friends. Today we're going to work on memory management a little bit, and we're going to implement this mechanism that I think is so cool from some Apple platforms, and it's called Purgeable memory. And what that is that it's a kind of memory allocation that you can get from the kernel that can be in a special state where it can be taken away at any moment without warning. And you can also set a flag on it that prevents it from being taken away. And the thing that this is so useful for is when you have something in your program, some chunk of memory that is nice to have, but if you lost it, you could recreate it, say like a cache of some kind, or like a big image that you could, say for instance, you decoded like a PNG file into a big image that has the raw pixel data, but you still have the PNG file. So if you lost the decoded version, it would be okay. You could still recreate it. Purgeable memory is fantastic for this type of stuff because it allows you to have the big allocation, but you set a flag on it that says to the kernel, if you ever run low on memory, just take this thing here. It's okay, I can rebuild it. And when the kernel gets low on memory, it just looks at stuff like this and says like, oh, well, I'm just going to take this away from this process here because he said that that would be okay, instead of having a bigger problem on your system, like having to kill someone, for instance. So yeah, that's what we're going to implement today. And there's one thing in the Serenity GUI that will benefit greatly from this, I think, which is that most GUI programs use double buffering for their window backing store. So this window that we're looking at right now, for instance, it has two copies of the stuff that we're seeing in the window. And it's always drawing into one of them and showing the other one on screen. And I'm kind of thinking that one of those, like the one that we keep in the back, but we only use it when we want to update something, we can sort of mark that one as volatile is usually the word used for this, which would say to the kernel like, hey, whenever this thing is volatile, you can take it away if needed. Of course, when this particular program here is not great because it's updating every second, but say that we had something like File Manager open, and it's just a static image, right? Basically the UI, unless you interact with it. So having two copies of this is kind of silly, but it's nice if we want to paint something different and then we have the backing image ready to go, but it would be okay if it disappeared and we had to rebuild it. So that's basically what I would like to do now, is make it so that the secondary bitmap that's used for each window is marked as volatile whenever we're not showing it on screen or drawing into it. And then if we wanted to, we could have some command that tells the kernel, hey, go and purge all of these volatile chunks of memory, and then we would see them disappear. And I guess we should have some kind of column here that shows how much memory in each process is purgeable and marked volatile. So I hope you understand the basic idea of this mechanism. So we're going to implement it now, and maybe if it's not clear now, then it will become clear as we implement it. So I guess first thing we got to do is figure out how you get one of these. And I'm thinking it's going to be a flag to mmap. So I know in Darwin systems you call some different API like mock VM allocate or something, but we're just gonna use mmap. So we'll have a different map flag, map purgeable. And purgeable itself, this is just a type of allocation. And then you're going to have to advice, I think, to tweak the volatile versus non-volatile state of it. Purgeable, it just means that it can be volatile or non-volatile. Okay. So we'll need to have advice as well. We haven't actually done advice yet. Advice is going to be, oops, wait, what the heck did I just do? Okay, give me a new one. advice is going to be important later on for improving malloc and stuff like that. But basically, madvice is just a way to tell the kernel, hey, for this range of memory in my address space, here's some advice for it about it. Here's what I'm about to do with it, or here's how I would like you to think of it, or whatever, like different things like that. I'm trying to put it always on top. There we go. So madvice void add, well, it's implicit size t and int advice. Okay, and we will just flesh this out with a quick syscall here so that we have something to call. Advise address size advice devices. Okay, advise, and then we just need to add it to process. Although we should look at what kind of constant we want. So mad normal, I'm guessing that that's 0 probably. We're just going to define some mad constant here. So we'll do mad volatile. Maybe we'll do it this way, that mad set volatile, and this will be like, what is this, an int? Do 800. Define mad set non-volatile, and this will be, I don't know why I was doing it this way. Something like that. It's probably fine. So these are just things you can pass these flags, and we don't allow passing both at the same time. Because you could imagine having like one of them be the bit on and the other one bit off, but that's just going to cause us trouble. Disambiguating situations where you're not passing either flag. So I think this is fine. And read. We should probably put these in Unix types. Yeah. Define map purgeable. Okay, and then let's just add sys advice. Okay, and let's look for m unmap or something like that. That would be a good place to put it. Or mprotect, even better. Very similar in spirit to mprotect. Process, sys advice. Advice. All right, and we're not going to do any region splitting or anything like that right now, or merging. So we'll just say, if we can find a region that is completely contained within this start address and this size, so any region that matches perfectly this, then we'll tolerate it. Otherwise, we'll say like, not valid. So that's a shortcoming. Same shortcoming in mprotect. We don't allow you to mprotect partial regions at the moment. So what do we want to do here? I guess if advice. Oh wait, hold on. Address. If advice madd set volatile. We can do something like this, and advice and mad set non-volatile. Return enval, because that's not valid. Okay, and then if advice mad set volatile is purgeable. If it's not purgeable, then we won't let you. There should be no volatility flag, so we'll just say enval again. Maybe eperm. And we'll do the same for non-volatile. region set volatile true, return 0. So volatile false, return 0. And what do we want to do in this situation? We'll say invalid otherwise, because like then it's some advice that we don't understand yet. So then another important thing is when you are when you set something to be non-volatile, that means that now I want to use it, right? Because that means that the kernel can no longer take it away from you if this succeeds. So once you do that, you really want to find out, while it was volatile, did the kernel yank it away? Like, is the contents of this memory still there, or do I need to reconstitute it? So we can either do that in the return value. That's one option. So we could return, we could say we return 0 if the if it was zapped in the meantime, or purged or whatever. Set non-volatile. So sniffly today. What should we do with this? We'll say let's return 0 if it was zapped, and 1 if it was not zapped. That's good. Okay, so if region was purged, then, or let's say was purged. If was purged, or return was purged. 1 means purged, 0 means not purged. Fine. And then finally, we want to restore this, I guess. So set was purged. False. Does this make sense? I mean, it was still purged. But now we're going to start, actually now, no, not purged anymore. Or, yeah, we'll do this. Okay, so now we need to add a few flags to region. So is purgeable. Purgeable was purged. And set was purged. Was purged. And then we also need, this volatile. Set volatile. Okay, so we need purgeable, was purged, and volatile. Cool. And then I'm thinking we should have some way to signal the system that it should purge everything. So I guess the easiest thing is just make a syscall. So this is purge. We'll just do this, and this will purge everything. Actually, now that I think about this, purgeability should be a VM object thing. It should not be a region thing. So, because region a region is just a piece of virtual memory, right? And it points into a VM object, which is the underlying physical memory storage for it. And this is the thing that's going to be like purgeable or not, basically. So let's make it a concept here instead. It's purgeable. So it's purged, and so we had all of these guys. We're just gonna move them over. So let's see. It's anonymous VM object. Maybe this could even be a different type of VM object. Now that I think about it, that's probably even better. So let's see. VM. Let's do a separate VM object. So purgeable VM object. VM. Purgeable VM object.o. Okay. And is purgeable is more of a VM object question that you can ask this guy, like, are you purgeable? Is purgeable. Because in purgeable VM object we'll have, okay, hold on. Pragma1's class, purgeable VM object, public VM, anonymous VM object. Man, it's so pleasant to use C++ in the kernel, I have to say. Like, having to do this in C would be so tedious. It's so nice to be able to build like these inheritance hierarchies and stuff. So no longer final, you get to be final instead. Because like a purgeable VM object is clearly an anonymous VM object, and this just fits so well. It's so weird how many projects there are out there that are doing C with classes, and they all have to go through this hoop jumping exercise, and why? Anyway, I don't mean to say that everybody has to do things my way, but I don't know, clearly don't need that flag. But it is rather nice to do things this way. So, volatile, let's say. And this is always true, and it's an override. And we can't even make it private, because you should never call it on a purgeable VM object. That would be silly. Okay. Now, we're going to have to look at anonymous VM object to see what kind of stuff we need to create here. So I think we need a destructor, and we need to create with size, and we don't need to create for physical range because that's just like a hack thing that we don't need to do with these. But we do need clone. Clone is that's what happens when you fork a process. Then we have to clone all of the or wait, hold on. Why do we need to clone a VM object? Do we actually need that? When you fork, we don't want to fork. Wait, when do we clone? It's for cow. Okay. I think we're not gonna for cow. Oh, I never thought of that. I guess we can cow purgeable memory. It's a bit weird. Weird interaction between concepts, but okay. probably fine. Okay, so we need these constructors, and what is this? This is just make non-copyable, make non-movable, basically. Although it's copyable with this constructor. Like, YouTube has been recommending me Star Wars things for the last few days, and I've clicked on a few of them, and I've been learning so much about the extended universe or whatever, things I never cared about. But it's just, I can't look away when they want to talk about, like, that one time that Darth Vader had a girl obsess about him. And I just end up watching this 20-minute video of someone explaining some obscure Star Wars book, basically, about that. And my brain is full of this stuff right now. And apparently Star Wars music comes out sometimes. So, anyway. It's probably okay, and then let's look in the CPP file. So this is really straightforward. We can just copy what this does. We're gonna have to tweak it a little bit, of course, but this is essentially the same as an anonymous VM object, just that it has a few extra flags, and we don't want those flags on the regular anonymous VM object because they are not relevant. So when we're copying one, we should probably copy over the flags. One option is that if you fork something and you have purgeable memory, then one option to simplify it would be to always, the child would always like lose his copy, but I don't think that would be very nice if we would always purge the purgeable VM object in the child. Let's not do that. That's not nice. Oh, the copy. This is private, you jerk. Well, we're gonna have to make these protected, or in the parent, I mean. Protected. Private. Okay, there we go. Now we should probably have the interaction here. So purge, we'll say. This will be where we call to in order to actually perform the purging. Purgeable VM object. So what the frick is going to happen when you purge? Now, just to be clear, like I've used these things on Apple systems, but I've never looked at how they're implemented, and at least not actively. I may have seen it a little bit, but I don't remember anything, just in passing. But the reason I say that is because I'm not exactly sure how we're going to do this, but I guess any VM object has a set of pages. So if you look at the VM object class, the base class of all of these guys, it has a fixed array of physical pages, and purging is all about taking these away. So we should probably also lock this VM object while we are taking them away. Just to make sure that that if we start purging a purgeable VM object and then we get preempted by the CPU, and then the process using this stuff wakes up, then we want him to take the paging lock before he tries to actually page these things back in. So he's going to get a 0 fault, which means that in the 0 fault handler, we're going to want to make sure we take the paging lock. I think maybe we don't do that at the moment, but we'll get to that. So purge is going to basically 0 out all the entries in the physical pages array. So we'll just iterate over it. How do you iterate one of these things? It's clear, but I don't want to do clear, do I? Or no, because that will delete the elements. I want to keep it the same size. I just want to iterate over it, brah. We have operator, okay, that's fair enough. So, I is m physical pages size. Physical pages I is null putter. I think this will actually free up all the pages. So now we just have to make sure that we take the paging lock. And the paging lock should probably be protected as well, so that we can access it from this here subclass. There we go. Okay, so while we purge, we hold the lock of the VM object. Now let's go just look at the 0 fault. Paging lock. So for inode faults, we get the paging lock, and this here gives me the heebie-jeebies, by the way. Like I feel like this can't be right, the way that we activate interrupts just so that we can take a lock and then turn off interrupts again. I'm pretty sure that that's not the right way to do this, but I also can't think of another way at the moment, so I'm just going to do the same for 0 faults. And 0 fault, by the way, is when we get a page fault for a piece of memory, and the thing that we want to do is just fill it with zeros, or provide a zeroed out page of memory in case none was allocated before. So we'll do the same here. The reason that we have to turn on interrupts is because when we come in here, interrupts are actually disabled. And this happens because when you get a page fault, then the CPU turns off the interrupt flag, so you cannot be interrupted while you're handling a page fault. Of course, your page fault handler can incur another page fault, which will then trigger the page fault handler again, but that's because page faults are actually exceptions, not interrupts. But that's almost like CPU trivia. Anyways. So now we have our haphazardly acquired lock. Where did I do that? 0 fault. Right, so when we get a 0 page fault, we take the lock, and then we don't need to acquire the VM object lock. Yeah, well, now we do, so. Then we check if we already have a page in that particular page entry. So we look at our set of physical pages and we look at the specific page that we had a fault in. And if it's not null, that means that another page fault handler probably already filled that in. This can happen if you are sharing pages between multiple processes. And then it's just a race, like whichever page fault handler, whichever process gets a page fault first, puts an empty page in that physical page slot, and then all the other processes that are using the same piece of shared memory, they're still going to fault. It's just that when they fault, they discover, hey, somebody already provided a physical page for this address. So he just updates his page tables here by remapping the page and continues. There's no actual page allocation if it's already been taken care of. So I was just thinking maybe we could actually take the lock after that. Because if somebody already filled that in, then we don't need to do anything. But maybe we should just lock it anyway. Probably better to lock early. So when we purge, because I don't want to get clever with the locks at the moment. There's plenty of time to be clever later. So let's just lock early, and then it will allocate a user space physical page, 0 fill it, put that in the slot, remap it, and then we've undone the effect of the purge of that particular page. So here we'll also say was purged is true. Okay, so how do we implement syspurge then? Like, how do we actually purge everything in some meaningful way? Let's make sure that we have a syscall for it. All right, syscall purge. I guess we can just walk all of the VM basically. So VM object. How do we walk all of the VM objects? Memory Manager has a list of them, I think. For each VM object. Well, aren't we in luck? Okay, so I think what we'll do here is we'll make a copy of that list. Vector ref putter VM non-null ref putter vector VM object. And we will disable interrupts while we are stealing this list of things. So for each VM object, VM objects, append VM object, just to make sure that nothing disappears underneath our feet. Okay, now we have a reference counting protected vector here. So for auto VM objects, actually we can say if VM object is purgeable, then we'll append it. And then we can even do like this purgeable VM object. I'm gonna have to include that header. Kernel VM purgeable VM object.h. Okay, then we can do VM object.purge. It's kind of cool because then we don't need to block interrupts while we are purging, because that would prevent us from taking the lock anyway. You can't take locks while interrupts are disabled. And the reason for that is if somebody else is holding the lock and interrupts are disabled, we're never going to get preempted allowing them to release the lock. So it would be a deadlock every time. Maybe we should return how many purges took place or something like that. Does this have any return value? I guess we can have a bool that says whether or not it purged something. And let's say int. Maybe it should be pages purged actually. Size t int pages purged. Purged page count. I think that's kind of cool. Then we can return int purgeable VM object and purge page count. If m physical pages I then increment the counter. Okay. Yeah, right, so in region now we have some things that don't belong, like these flags here. They don't make sense. And then in advice, these flags need to go on the VM object. So we can just do this. And oh, and we need to cast it actually. So we can do this static cast to Purgeable region VM object. Set volatile. Oh, I didn't add that. Set volatile. Ooh, B. Volatile is B. And set was purged, I guess, is gonna just do this. Okay. Now we're going to need a simple user space program for this. Let's call it Purge CPP, I guess, something like that. And is Purge. I need to expose this. We'll just do the kernel thing directly. And then printf purge page count d purge page count. Okay. Can we actually build this purge CPP? Seems like we could. That's cool. But the kernel don't build, so. Set was purged. That it does not have a return thingy. All right, now okay, so how do we test this? I guess we want to make some allocation in a little test program just to start with. So we have the purge program. Now let's also make like a little goofy program just for this. So we'll just call it goof. Okay, so it's going to be like this, and let's open it here. Goof. And what this is going to do is that he's going to allocate a piece of memory, some purgeable memory, and we will get it by calling mmap. We'll ask for 1 megabyte, and we'll say prot read, prot write, map purgeable. I think when you originally map purgeable memory, will give you non-volatile. And no file descriptor. Okay, and then we'll just assert the pmem is not map failed. And I guess we should include ACK assertions for that. Okay, and then we will say got pmem p, and then we will make it volatile. So we'll do pmem specify the whole thing, mad set volatile. Okay. And we can just do something like this. If it fails, then pair turn 1, and then here we will just go into a loop and sleep. Marked it volatile sleeping. And I think we're gonna wake up in our loop and check if the memory is still there, maybe? So we can do that by marking it non-volatile, and that will tell us if it was changed or not, if it was taken away. So we'll do something like this, int rc advice. So if rc is less than 0, something went wrong. So advice mad set non-volatile. I guess we should have said something like that up here too. And we'll say if rc is 0. What did that mean again? I already forgot. This is madvice. Madvice. If it was purged, you get 1. Okay, so if rc is 0, print not purged yet. Else printf purged since last. Okay, and then I guess we'll just remark it as volatile again. Set volatile. And same complaint here. Okay, and then we'll just loop like that. It's kind of cool. Undefined reference to madvice. Well, I'm terribly sorry. Oops. My alarm. I admit I set an alarm because I thought I was going to take a nap, and then I lied down for like 5 minutes and I got up again. Afternoon naps are dangerous, man. I just feel like I get more tired if I take a nap. Somehow, every couple of weeks, I think maybe I can take a nap. It's never a good idea. For me. But I'm sure in a week or two I will think so. So, let's see. Oh, we died. Why did we die? Oh, frick. Interesting. I was just adding this earlier today. It's already finding a bug, but it's not the kind of bug I want to debug right now, so we're just gonna remove this assertion here. And now we have 2 of these. And what can we do with this? Goof. Okay, so we got map failed already. Why did we get that? Symmap. Oh, I guess we're getting the purgeable thing, and we don't know what to do with it. So we gotta pass in map anonymous. But maybe purgeable should imply anonymous, or no. We definitely need to set purgeable here and make sure that we create a purgeable piece of memory. Totally forgot about all of that. So I think we'll start with something like this. So if it's purgeable, I'm going to say allocate purgeable region. And everything else could kind of be similar. Can purgeable memory be shared? I guess. Can it be a stack? No. No purgeable stacks, dude. What the heck? That's too weird. Okay, so now we need a allocate purgeable region, which is just the same as allocate region with VMO, which is allocate region with a specific VM object, because we're just going to create the VM object that we want. I think so. Maybe we can actually, instead of doing allocate purgeable region, we'll just say allocate region with VMO, and we will make a VM object before we call it. Wait, where's the past? Okay, well, let's just make the VM object. So, purgeable VM object. Create with size. If VM object return enomen. Oh, we have to return it as a void star, I guess. Deleted operator. Oh shit, does this return a non-null ref footer? Well, that's probably not the right thing to be doing, but alright, we'll deal with that later. So let's see. Oh, I wanted to look at this prototype. The VMO is the third argument. Okay, so third argument, VM object, and then wait, offset. Oh shit, we need an offset. An offset into the VM object. That's just 0. And too many arguments. Well, whatever the last one is, we're not going to pass it. I guess that's commit, yeah. Whether or not we should allocate physical pages right now, I would say it's okay to delay that. Okay, so now Purgeable should give you a Purgeable VM object. Maybe we'll say Purgeable mmap here. Mmap Purgeable. Something like that. And dump regions. I'm thinking dump regions we should print out if it's purgeable. So like if VM object is purgeable, we'll say P and actually maybe we should even show the volatile flag here. So maybe another character in case it is purgeable. Then we will do region VM object. Oh god, this will be messy. Okay, let's not worry about that one right now. So we will just do that one and let's see if we can get this even running. That would be nice. So goof. So now, oops, now we have some purgeable memory. Purge, and it's been purged since last, but we got no pages purged. And that's probably because we didn't actually force the kernel to provide any physical memory there. We just made a VM allocation, but we never used it, so it was very lazy and didn't allocate any memory, any real memory. So we'll have to fix that by, you know, just putting something in it. We can just memset it, and it will be forced to put something in there. We're forced to give us some frickin' physical memory. You know, I have to say, I'm learning so much about all of these things by implementing them, because it's fun to have to think about how all these things actually work. And implementing stuff is really the best way to learn how something works, in my opinion. Okay, so let's look at this process now in the, if we take the goof process here and we look at the memory map, we can see, we don't see more information. We should add more info here, but we see that it's a purgeable piece of memory and it has 1 megabyte resident. So I'm curious what happens now. Wait, did you just switch? Not cool, bro. Okay, that's an annoying bug. Let's see what happens if we purge. The resident memory should go away if I understand my own code correctly. Look at that. The kernel took away all of that resident memory. That's pretty neat. So, now of course, what would happen if you, this memory is still accessible to you? I feel like maybe while it's in the volatile state, we should make it not readable, not writable. Or maybe it should just be undefined behavior if you try to use it while it's in that state. But it's probably a lot easier to deal with this if we don't let you, access the memory while it's volatile. Because the point of volatile is that the memory is there, but it might go away, but you don't need it right now. That's why you make it volatile. So probably it's always a bug to try to access the memory while it's volatile because you don't know if it's there or not. So let's start by just exposing this in the memory map widget though in system monitor. So let's say we'll add a letter for this. Maybe we should even make our own field. Actually, we can make our own field for this. So let's say purgeable, and if it's not purgeable, then we'll just have nothing in this field. Otherwise, it will say volatile or non-volatile. Volatile. If volatile, then filler append volatile. Wait, how does this work? Just return a string. So if purgeable is false, then in the purgeable field we will show nothing. Otherwise, volatile is true, we show volatile, otherwise we show non-volatile. Okay, now we just need to expose these flags in the procfs entry for the memory maps. So procfs pid vm, here we are. So readable, writable, stack, blah, 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 blah. For each region, we'll show purgeable is purgeable if region object, or no, if region VM object is purgeable, volatile, it's going to be static cast purgeable VM object, region VM object, and is volatile. Okay, so I think this will give us another field in that list that shows the purgeable. If a piece of memory region is a purgeable region, then we will show volatile and non-volatile. Otherwise, it will be empty. That would probably be good enough. So what's wrong with you here? Cannot static cast because you would be losing the const qualifier, Andreas. Jeez. How could you not see that? Okay. Purgeable memory, by the way, is, in case you don't know this, it's a very, very important mechanism on macOS and iOS for dealing with processes, memory consumption, and for like having sensible memory usage policies, because this allows processes to be a little bit greedy with memory, because you can be greedy with this kind of memory as long as you make it volatile while you're not using it, because then you are just using memory that's available, but once the kernel decides that he wants it, it's just free to take it away. And the magical thing about this, I guess I should have mentioned this before, is the thing that makes this so magical to me is that the kernel can take away this memory without asking the owner. There's no interaction needed. Like, you don't need to wake up the owner process. It doesn't need to run. It doesn't need to like do any kind of cleanup or freeing or anything. It can just be taken. And that's really, really magical, especially in systems that do any kind of swapping, for instance. In fact, any time that you can take away resources from a sleeping process without having to wake it up, that's really, really good, because waking up a sleeping process that has swapped anything out to disk or to compression pager or whatever, it's super heavy, and you really want to avoid that. So this type of thing where you can recover resources without interacting with the process. Ace. Anyway, so let's see how we are doing now. So we'll start the goof process, and should learn to get system monitor down here instead. Way nicer. And where are you, goof? Right here. Okay, so now this is volatile. And that's good. In fact, we should probably show it up here too, like the amount of purgeable volatile and purgeable non-volatile in the process. Because essentially, once this mechanism is working correctly, then a piece of purgeable volatile memory in a process is way less damning, if you want to call it that, towards like the process's memory footprint, because you can almost subtract it basically, right? Because it shouldn't contribute to the process's footprint. Anyway, let's purge and see if we can. Where's goof? Right here. Let's make those resident pages go away. Bloop. That is so neat. Okay, let's make it show up in the big table as well. So this is in procfs all, I think, the big monster where we show everything. Let's show the amount virtual, resident, and shared memory. So we'll also show the amount volatile, amount purgeable volatile. Or you can just say amount volatile. Maybe this is better. We've got to be clear with what's going on here. So purgeable volatile, purgeable non-volatile. Then to count these, we got to look at, let's see, purgeable volatile. We walk all the regions, and if region VM object is purgeable, if it's not purgeable, continue. Otherwise, Or wait, hold on. If it's purgeable and static cast VM object, purgeable VM object, is volatile. And we will add region amount resident. That makes sense. Okay, so that's just the amount of resident memory pages in that region, if it is volatile. We'll do the same with non-volatile. So if it's purgeable and volatile is false. And then we'll just add these two functions. Could probably produce this statistics in a way more efficient way than walking all of these things over and over. There's a lot of inefficient algorithms going on, but it's not like it's the biggest problem in the world. So now, amount resident, where are we sucking this out? In the C process statistics reader, right? Amount purgeable volatile. And we are just gonna populate those two here. So purgeable volatile and purgeable non-volatile. Okay, now these should be available to us in the process model, I think, or wait, am I thinking right? No, I have to add them here as well. Okay. Well, no big deal. Just copy them over. And we are almost there. Of course, we need to add it as well. So what do we call these? Virtual. We have virtual, physical, and then we could have volatile, purgeable volatile, purgeable non-volatile. Yeah. Okay, I'll need to add these in a bunch of places. So what should the labels be for these two kinds of memory? I'll just call it volatile, non-volatile. We call it Purge P vol, or Purge V, Purge NV, something like that maybe. This is getting kind of crowded up there in that UI, so I'm just in the interest of keeping things short and sweet. And we'll, no, Purge V and Purge N, that's good. I know what those are. Okay, and just the alignment here, so purgeable, these are numbers, so they should just be right aligned. And then we gotta extract the numbers. It's still pretty tedious to add fields to this, to the system monitor, but it's not that bad, but it could be easier. Physical, oh, pretty bite size. Sounds like I've been here before to make things pretty. I guess this is just something that formats it saying like kilobytes, yeah, like, that's kind of neat. Okay, so I think this should put everything into the system monitor. Now, I was thinking that the next thing is that we're gonna do this to the those bitmaps that we were using for the backing stores for all of the windows. So G window. Bitmap, because every G window has a front bitmap and a back bitmap, unless you turn off double buffering, in which case it will only have a front bitmap. But normal situation is that you have a front and back, and the back bitmap is the one that we're drawing into in order to create the next look of the UI. And then once you're finished drawing, then we'll swap them. So now what was previously the front bitmap becomes the back bitmap, and vice versa. And when that happens, then whoever becomes the back bitmap, we should mark him as volatile until we want to paint again. So let's see how we actually do this. Create backing bitmap. I think this is the function that we call to make these. And this just calls create shared bitmap. And that calls create shared buffer. Oh, it uses shared buffers, right. So that's a bit tricky because we've been doing this for mmap, not for shared buffers. Shared buffers are their own thing, and they have their own APIs. But nothing says that we can't extend the shared buffer API with this mechanism. But we should probably commit this before we go any further then. So there's a whole bunch of stuff here. Let's just see that this is kind of working. Goof. And now we can see the purge v, purge n. And right here, we have this guy with his volatile megabyte of memory. And if we put him up top, really freaking nice. And I guess we should just verify that it works if we don't mark it volatile. We just do this and this. Does it show up in the other column? Just to check. Yep, it's here. Okay, so yeah, and this basically tells you how much physical memory is used by this process. But the footprint, if you want to think about it that way, you could say, I mean, in this case, actually, because it's non-volatile, then it contributes to the footprint. But if it would be volatile, then it should not contribute. So what happens if we purge while it's non-volatile? Ooh, it got taken away anyway. That's not very good. That's not supposed to happen. Why did we take it away? Because we don't look at the volatile flag. Or we don't? Who calls purge? Sys purge. We just look at is purgeable, but we don't look at is volatile. Jesus, what a horrible jerk I am. Okay. So here we should this thing will take the paging lock, right? Yeah, so after we take the paging lock, we'll say if volatile, if it's non-volatile, return 0. Okay, see, we almost made a really dumb mistake here. Okay, now, goof. And purge non-volatile, there he is, goof, and purge, and it stays. It's more like it. Okay. So first off, let's not get that device change. And then we had all of these changes. Commit a. My goodness, this is a lot of changes. We don't have to do the. We can only do the kernel actually. So kernel and the madvice is called. Commit kernel add start implementing purgeable memory support. It's now possible to allocate purgeable memory using mmap with map purgeable. Get purgeable memory by using purgeable memory has a volatile flag. We set using madvice. And set volatile on volatile. Setting it to setting the flag to non-volatile. Setting a purgeable region to will return whether or not the memory has been taken away by the kernel since it was last taken away by the kernel while volatile, while being volatile. Okay, so the magic of this kind of memory is that this, when in the volatile state, the kernel may take away the underlying physical memory pages at any time without notifying the process, the owner. This makes it possible to, this allows you to cache very large and expensive things guilt-free. Or guilt-free, I don't know, it's a guilt discount. This gives you a discount on guilt when a guilt discount when caching very large things. Basically, if madvice set non-volatile, I have to look at this thing again. Was purge returns 1, right? Returns 1, that means the memory was purged while volatile, and whatever was in that piece of memory needs to be reconstructed before use. Okay. And then we'll say purge commit purge. Add a small command line utility for purging all volatile memory. System monitor. Show information, expose, show information about purgeable memory. This patch adds some exposes some fields about purgeable memory regions, and we now also show total purgeable non-volatile memory in the big process table. Okay, so let's look at shared buffers now. Shared buffers are the mechanism where that we use to create bitmaps that are created by a client program and then shared with the Windows server so that the Windows server can draw it to the screen. That's using the shared buffer interface, and that allows us to not copy bitmaps from a process to the Windows server, but they're just shared instead. And right now, they are all using the shared buffer. This is just a convenience class that does the syscalls for you. So I'm thinking that we could even make it so that all shared buffers are purgeable, and then by default they're all in non-volatile memory, and that would just make it kind of easier to deal with this. I think that's probably okay. So shared, create shared buffer, is that it? Shared. Yeah, create shared buffer, right. Create shared buffer. It creates a shared buffer object in the kernel. And what that does, it makes an anonymous VM object. So we are just going to go here and be like, you are now a purgeable VM object. And then we will have a way to say, we can query, or wait, what if we just want to get to the VM object from it? I guess we can do something like this. VM object, const, something like this, and we'll just change this type here to be purgeable. Now, we'll need an API for this. So let's look at what APIs we have for syscalls already. I mean for shared buffers. So shared buffer. We have create shared buffer, get release. This is for the reference counting of shared buffers. And then we have get shared buffer size, tells you how big it is. Seal shared buffer makes it read-only forever. So we're going to need some new ones. We're going to say enumerate syscall. Set shared buffer volatile. Something like that. I feel like that would be kind of sensible. And then, yeah, that's good. Sometimes maybe I feel like they should be called SHB or something like that, set volatile. Or maybe shabuf. Set, maybe shabuf is not bad. Kind of regret these long names. Should go through and change these laters. Shabuf get size, shabuf seal. Yeah, shabuf is better. Let's call them shabuf. Or do I like that? I guess I kind of like it. Shabuf. At the same time, I don't want to invent terminology if I can avoid it. So shared buffer set volatile. Ugh, fine. We will do it this way. Whatever. Get shared buffer size. Set shared buffer volatile. Volatile. Oh, can't be using that term because it's a language keyword. Come on, Andreas. Get shared buffer size. Okay, we'll put it next to this guy right here. State, let's call it. Okay, and this here is just getting the shared buffer from the big list of shared buffers, basically. And verify that we have access to the shared buffer, otherwise that's a no-no. You can't be accessing shared buffers that are not yours. And then we can log something like set shared buffer d volatile is you. Oh, that's pretty good. Resource size, say state. And then we will do shared buffer dot VM object dot set volatile state. And bool was purged. Shared buffer dot VM object was purged. Return was purged. And then we should probably clear that flag, right? I already forgot how we did this in the other place. Set was purged false, right? Oh shit. This is a little bit confusing, I have to say. Like the fact that we cleared the was purged when you make it volatile again. I mean, this should only happen if you're making it non-volatile. Oh, right, yeah. So if state is false, then we're becoming non-volatile. If state is false, oh man, this is so weird. I'm almost thinking if we should have 2 syscalls for this, but that's so overkill at the same time. So if it's false, we'll return that. Else, don't need to do else after a return. If you're making it volatile, VM object set volatile true. There's nothing else to it really. That will just succeed. Okay. So set shared buffer volatile. Let's incorporate that in the wrapper class here. So we'll say void set volatile bool b. Efficient set volatile and bool set non-volatile. No discard. And when you set non-volatile, you have to actually look at the return value, and if it returns true, that means that it was purged, and you have to do something to refill that thing. Okay, I think that's somewhat sane. And maybe we can just be lazy here and get the kernel syscall interface. Let's see. Set shared buffer volatile. Shared buffer ID true. And we should just assert that RC is 0, actually. That's probably okay. And for non-volatile, if it returns 1, then you have to change it. Or what should the semantics be? 1, then you don't have to change it. if set non-volatile returns true, then everything is good. That's how I feel like the ABI should work. So if it returns 0, then everything's good. No purge happened, return true. Otherwise, return false. If RC is 1, return false. Assert not reached. Okay. All right. And then let's just see if everything's fine this long. So now, without changing anything else, things should still work, and we should see all bitmaps showing up in System Monitor from every GUI app. Every shared buffer, every shared bitmap should show up as non-volatile, purgeable memory. So let's see that that works. And we can just go and look a little bit here. Create shared bitmap, blah, blah, blah. So it's really where we are messing with the back bitmap, front bitmap stuff. Where are we swapping them? Swap, right, swap. So here, when we actually go and swap the front bitmap and the back bitmap is now, wait, hold on, what are we doing here? Copy whatever was painted from the front to the back. Yes, and then after this point, the back becomes volatile. So it will be something like back bitmap, shared buffer, set volatile. If double buffering enabled, let's say. If it's not enabled, then we don't have front and back, so we shouldn't be doing this. Although maybe we won't even call flip if we don't have this enabled. Yeah, okay, so then it's okay, we don't have to think about that here. And then where do we start to draw into the back bitmap? Because that's where we need to actually start worrying again. Multi-paint. So it's created new backing store, blah, blah, blah. If we don't have a back bitmap, then create backing bitmap. So I think that, let's see, this is if you resize the window, then we throw away the back bitmap and make a new one. So I guess if we don't have a back bitmap, then we create a new one here, but if we do have one, if we did have one, we gotta make sure that we mark it, well, non-volatile. Get pixels. Still have pixels. This is an mback bitmap. Shared buffer set non-volatile. If we don't have the pixels, then we gotta copy them over from the front bitmap. And if m front bitmap and m front bitmap size, back bitmap size, and copy back bitmap bits, and front bitmap bits, and back bitmap size in bytes. So just copy everything from the front bitmap. Otherwise, I guess we'll just create a new back bitmap. That would be if we don't have a front bitmap that we can copy from for some reason. So I'm not actually sure how that would happen. unable to use front bitmap after losing back bitmap. That's a really weird scenario. I'm not sure if that would happen, but at least we'll log if it does. Okay, so now everyone's backing store is purgeable and non-volatile, including the Windows server, as you can see here. The Windows server, of course, shares these bitmaps with the clients. So the Windows server's amount of purgeable and non-volatile is the added purgeable and non-volatile from the different clients. Terminal right here, 800 kilobytes or so. Will be kind of interesting if we could get it to purge all that. Okay, so let's see if my little modifications here worked. Somehow I feel like this is going to be very crashy, but it'll be interesting to see if we can make it work this easily. But yeah, basically, this is when we want to paint. So this makes it impossible, more or less, to paint out of turn or out of order. Like if you try to paint into the backing store of into the back bitmap of a G window, then we shouldn't be doing that. And let's see. So far so good. We're live. Let's get this thing up. And look at all these volatile memory. Like this will all go away if I hit purge. But what happens if we do? We're still alive. Still running. And purgeable and non-volatile still. We have file manager has one bitmap at least left. But what happens if we open him? We make him draw a little bit. Oh, look at that sadness. Oh, shit. Okay, well, we didn't do everything right, that's for sure. So, we got all crashy on us. Okay, well, what can we do here? So, what do we actually have going on? Right now, file manager has all this non-volatile memory. Wait, why does it only have 400? It should have a non-volatile version of the contents. Why doesn't it have that? After we swap, then the front bitmap needs to become non-volatile. Wait, am I messing that up? So where do we flip? Current backend bitmap. So when we swap, the front bitmap is now the back bitmap. And then the former front bitmap becomes volatile, but before we swap, we need to make the back bitmap that we've drawn into, it needs to become non-volatile, but it should already be non-volatile from us entering into the paint. Wait, why would the front bitmap? I'm confused. I feel like we have two volatile surfaces here. Let's look at file manager. Oh, look at all of these. Every little, every icon that we loaded, I guess, ends up in a non-volatile shared buffer. It's kind of interesting. So these are the two backing stores for the window, I bet. both non-volatile. We redraw a little bit. Why are they both non-volatile? One of them is supposed to be volatile. Jeez. So I'm definitely not thinking right about this. Now they're both volatile. All right, I'm not braining right. Because both of these calls set true. Oh, jeez, I'm such an idiot sometimes. I'm so sorry if you saw that while I was doing it and you've been waiting for me to discover it. It's kind of fun, though, to see, like, when you make this kind of mistake, like this copy-paste mistake, which is one of my biggest sins, it's fun to see how the system acts when you have this kind of mistake in place. Because once you figure out what the mistake is, it sort of gives you this aha moment, like, ah, that's why it would behave like that. This explains this totally goofy behavior. All right, so what do we have now? Now we have half and half, right? So that makes sense. And the back bitmap should be volatile at this point. So if we scroll down here, I mean, we can't tell which one is back and which one is front. We could probably actually teach it how to show that here. But anyway, what happens if we purge? So now yoinked away the volatile memory. But we can keep on living. Although we had some artifacts there, that was not good. So, due to illegal instruction, oopsie doopsie. Why are we getting illegal instruction, I wonder? Okay, so behavior is not perfect. It would be good if there was a way to set the name of a shared buffer. I guess we don't have that API, so let's just add it. Set shared buffer name. And shared buffer. Okay, we'll add this. String view is better for this actually. Characters without null termination. Syscall process. I want to see which is which here. Okay. Yeah. Name length. If validate read name length, return e fault. Then we need to find the shared buffer. Loop. Oh shit, how do we find the name of this guy? I guess the name is actually, it's not the VM object that has a name, it's the, does VM object have a name? No, it's the region that has a name. So then setting a shared buffer name, we don't need a syscall for that. We can just or maybe we do need a syscall, but we don't know where it's mapped in our memory, so the syscall is weird. mmap set mmap name, I think we have to use. Data m size name. Ugh. Then we have to use the silly string instead of string view, but that's okay. It's not the end of the world. I wonder if we can actually do this or if this is going to fail. We'll see, but don't need that guy. And set volatile, blah, blah, blah. Now we will set the names of these guys. So we'll say like mback bitmap set shared buffer set name back bitmap. Okay. Something like this, I'm thinking. I feel like this one is going to freak out on me because I didn't allocate this memory with mmap, and I'm trying to set the mmap name. So I'm just going to disable that check right now. G window. What were we doing? Create. When you create a new backing store, we need to store this information somewhere. The fact that we created a new one, because if we create a new one, then we repaint everything. So maybe we can just simplify it to do this instead. Maybe so. If we don't still have the pixels, we can make a new backing store. That would work too, I think. Let's just look at these names now to see how they show up. File manager. Loop. Oh. Why don't you show the new names, bro? I guess this didn't work. Oh, I'm a bit surprised that didn't work. Name shared buffer. Where does that name come from? Shared buffer. Okay, well, let's try this other approach here, where if we lose the pixels, we just create a new bitmap. So I think maybe I was trying to get too fancy with like copying the pixels from the front bitmap. I think that's just I don't know why I was even trying to do that. We can also just create a new bitmap in the case we lost it, because that's what we have to do anyway. We don't have any physical pages left. They've all been taken away. So this is supposed to be kind of a rare situation, you know? At least that's kind of how I think about it. Okay, so file manager. I wish that we could see the names down here change. I don't know why they don't change, but it's a whole other thing. So let's try to purge. So this one seems to have been fine. This one's fine. No weirdness. What if we purge again? Okay. So I think one thing is that we were definitely losing our cool there a little bit when copying into the thing. What we didn't do it the old way. What was the old way? That we would try to copy the front bitmap to the back bitmap. But I bet you that's because we didn't take care of the page tables when we did this. So when we do this, we have to take care of the page tables. That's why that's not working. So let's leave this here so that we cause the bug. Because I think the problem is we tried to copy the front bitmap to the back bitmap, and because the back bitmap no longer had the physical memory, it was supposed to get page faults so that we could populate it again, but we didn't get page faults because we'd never told the page tables that we had removed that memory. So when we purge, we have to actually we have to find every region that refers to this purgeable VM object and remap it. So this is going to be a bit of a cumbersome operation. Can we walk all regions somehow? For each, do we have all regions somewhere? We have all the kernel regions and all the user regions. They're in a list, so we can definitely walk these lists. Oh, we have for each region. Great. We're going to have to walk this guy and remap every single region that refers to the purgeable VM object as being purged. So I think after we've purged, maybe before we purge, we gotta remap these regions. So, or no, let's do it after. Otherwise, it won't make any sense to the remapping logic. Because the remapper is supposed to discover that, hey, there are no physical pages here. I gotta map this as that we would fail if you try to access it, if that makes sense. So mm is memory manager. For each region. Why can't I get to that? For each region. Oh, it's a VM object thing. Oh, wait, hold on. So for each region. Oh, duh. It was right here all along. So for each one of my regions, region dot remap. Is it that easy? Remap? Ooh, look at that. We have remap. Just maps itself in the current page directory. And then it looks at the physical page pointer. If it's false, we go here. We say not present. Yo. That's cool. So you'll get a not present page fault. That's pretty rad, actually. Does this expect us to have interrupts disabled? I forgot to look at that. It will disable interrupts for us. Okay, that's fair enough. So now it should be able to work without trickery. Why was share buffer set name not working though? That's suspicious. Set name. Set name. Set a map name. Very suspicious. Why don't you go anywhere? Well, whatever. For each region, that did not work out. Is used but never defined. Why don't I understand what the problem is? Oh shit, it was implemented in a CPP file. It's a template function implemented in a CPP file. That's not going to be visible to us over in Purgeable VM object. It has to be in the frickin' header. Oh, I see. And then we can't use it here because it accesses the memory manager. So we have a circular dependency problem. Well, we'll just put it in the memory manager header. Boom. Okay. This is something that's a little bit sad about C++. Is, if you have circular header dependencies, then it becomes necessary to put things where they don't belong sometimes, like VM object. A VM object function clearly does not belong in memory manager.h, but because I cannot put it in VM object.h, I'm forced to put it here. And the reason is that memory manager.h includes VM object.h, and I can't include memory manager.h from here because then they would include each other, but this function requires the memory manager internals. So, a bit annoying, but we walked around it. Okay, so now we have the copy front bitmap to back behavior in place. And let's do a purge to see what happens. Do we lose our shit, or do we just carry on? We just carry on, because the remapping was exactly what was missing. Cool. Dude, this is so freaking neat. Very, very, very neat. Yeah. So it's so cool, like, if I click around, like, if I purge, and you look at File Manager, now he has no volatile memory. His total physical footprint is 2.7 megs, right? But if we click around here, so it redraws, then it has to allocate about 1 megabyte backing store to redraw the window. Now the footprint has grown to 3.9 megs. But as long as we purge, and they go away, and then, of course, System Monitor redraws almost immediately, like the next time the UI updates. So we have to actually update we have to repaint. So awesome. Let's look in the memory map here. Volatile. Oh, and can we see them flipping which is which? Oh, if I'm resizing, then actually the address changes because it has to allocate a new backing store. But I guess these two guys are the front and back bitmap. The name not updating, we'll just ignore that. We'll revert the change, but very interesting. So let's just verify that it doesn't screw up something like Snake, which uses it has double buffering turned off. So if you purge, it will still survive. Yeah, so Snake keeps drawing, but it never has any volatile memory because double buffering is not turned on. It's been a while since I was playing Snake. Ah, this is so cool. Let's see what kind of changes here we want to commit. So this change that I was making to facilitate setting the name of a shared buffer, let's just undo that. Because we don't want you setting the name of something that's not an mmap. Okay, set shared buffer volatile, blah, blah, blah. Shared buffer now uses Purgeable VM object as its backing store. Cool. Shared buffer volatile is now its own thing. Shared buffer set name. Let's lose it. Okay, now I'm just thinking, should we actually keep the front bitmap? I think we should just make a new bitmap if the old bitmap is thrown away, because it's simpler. I just put it back so we could test and fix the behavior before we had the page tables updated. So, multi-paint. Let's say that if the memory was purged, and we don't still have the pixels, then we will create a new backing bitmap. Oh wait, hold on. Oh shit. I was actually always creating a new backing bitmap here. So, was I not testing the right thing now? Well, then we gotta double make sure. Because now I was always creating a new back bitmap. So, I was not testing the right thing. I hope it still works, otherwise we have some more debugging to do. And of course we have a big chunky rebuild again because I changed the syscall headers. Is there any more diff editing we can do in the meantime? Lib C. Can get rid of this one. Oh, we don't need the string class here, actually. Let's keep on rebuilding, brah. Alright, come here. Let me purge some stuff. Shit. Oh, it's that device thing again. Damn. Well, it's good that I have that assertion. I have to debug that later, but right now it's just getting on my nerves. So, purge, and does this screw everything up? It does not appear to screw everything up. It works. yeah, sometimes you get 0 if nothing was purged, because there was nothing volatile. But I really love this. This is so cool. Purge. Wait, where did it go? File manager. I almost feel like we should make a special column that shows how much private dirty memory belongs to each process, because the amount of physical memory, it's sort of offset now by the it matters less how much physical memory a process takes up when some of it is available for the kernel to take away. Of course, now we haven't implemented automatic recovery of, or automatic purging. We're only doing on-demand purging with Purge syscall. But in the future, we should also make it so that, for instance, imagine that the kernel wants to make a page allocation but has no more pages available. Instead of saying, hey, I'm out of memory, start crashing and panicking or whatever, we just take whatever we can recover that's volatile. That will be a fun thing to implement some other day, but right now we are just going to turn this into some commits. And I'm immediately going to undo that device change because I don't want to commit it. And in gwindow, let's actually do that way so that we do create a new backing store if we lost the pixels, just for simplicity. Okay, so git add dot, or is there anything here that I should have known better about already? Yes, this one. We should always remap on purge, so let's do that one separately. Kernel. Remap all regions referring to a purgeable VM object on purge. Otherwise, we won't get page fault next time you try to access the purged purged memory, let's say, yeah. And then this was just moving this guy to memory manager.h, right? Yeah, so we can do that in a separate commit. Move VM object for each region to memory manager.h. It can't be in VM object.h since it uses depends on okay, and then syscall, we are adding share buffer volatile. Okay, so here now, git add dot, git add libraries libc shared buffer cpp and h kernel plus libc allow make all shared buffers purgeable default non-volatile. Purge makes shared buffer use a purgeable VM object as its underlying memory storage memory object. A new syscall is added to control the volatile flag. will make it possible to do. We don't need to explain because it's a patch coming up very soon. Shared buffer. It's pretty cool. Is there anything here that did not belong? No, not really. Okay. And then finally, set non-volatile. Yeah, it's fine to call set non-volatile. It doesn't do anything, actually. If you, I guess we can just do something like this. So if m double buffering enabled, because then in an app that doesn't do double buffering, we don't even bother, because we know that we have a backbit map, and if we don't have double buffering, then it won't have gone away. So we don't have to do anything. So we'll say libgui. Mark G window backing stores as volatile while not painting. We now take advantage of the support for Purge of shared buffers being purgeable memory by setting the volatile flag on window backing stores window back buffers. Window back buffers while not painting into them. This note that this is only only relevant for when double buffering is turned on, but since that is the default, this does affect. This is the common scenario. This does affect most apps. Basically, I don't know, this means that one of the two backing stores used by each window is purgeable volatile most of the time, allowing the kernel to purge it, recover memory if needed. Purge to recover memory, yeah. This we could you know, we could do even better with this. Like if you minimize an app, for instance, we could even have the primary, the front bitmap could also be volatile in that state. Now that I think about it, that would be kind of a cool thing to do as well. But I think we're not going to do that today because now I'm getting a little bit tired and we made a lot of progress, so I think we're good. Let's bring up something fancy like the browser. And let's do some purge. Nothing crashy, nothing bad. And we can see browser guy right here. Go to a page that has a lot of stuff on it. Like this happy birthday page. I'd like to open it. Of course, all of the bitmaps that we open, they're not going to be purgeable, but that would be a very good thing to do in the browser next, is to, when we decode all of these PNG images that we download. Oops, we crashed. Why did we crash? Shit. Crashing the PNG decoding. Okay. That's not what I was working on today. I haven't seen that crash before. So let's chalk it up to a fluke and try one more time. That's a bit weird. I wonder if this address, it's definitely not in the address space here. Wonder what went wrong. Something is not right. Let's start over. Come on, browser. Don't be this way. I mean, these are definitely not bugs in the stuff we were working on today, I think, because this doesn't use any of that. It's only the window backing store here now using purgeable memory. But as I was saying, we could, in the future, download PNGs and then decode the PNGs into purgeable bitmaps. And then you could imagine that we would just allow you to purge any PNG, any decoded image that's not on screen at the moment. Could be volatile, for instance. So like this one would be non-volatile right now because if I scroll, we need it to repaint. But anything that's not visible in the viewport, we could make volatile. That would be kind of cool. So I guess it is finished loading, and I just want to purge, see what happens, just because it's fun to purge. Now we died. Oh, because of the device thing. Oh. Damn it. I just wanted to see browser purge. Why does it have to be so difficult? Well, I can just say my outro anyway. So I think this is going to be the end of the video. So if you made it this far and you're still here, then I thank you for watching. And I certainly hope you saw something interesting today. And maybe you learned about purgeable memory and volatile, non-volatile stuff, which I'm very happy if people learn about this because it's a really cool mechanism, I think. And I wish that more things would use it. Now we have it too. So thank you for watching and hanging out. And we're going to do a purge. And everybody survived. It's awesome. And I clicked on it and it loaded. Aha. So maybe I could take this opportunity to say that you can sponsor me on the SerenityOS.org website. We have this little page that talks about GitHub sponsors, which is a program that I am now in. If you enjoy my work, my videos, content, and so on, then check that out. And of course, I'm also on Patreon if you like that kind of thing. And I'm going to stop filling the time and say thanks for hanging out, and I will see you next time. Bye.